All right. So what is the law of conservation of momentum? Well, conservation, as we know, means to stay the same or to keep, right? So the law of conservation of momentum states that when two or more objects collide, their total momentum remains constant, provided that no external force acts on them, okay? So in other words, if you have a crash or a collision and the only two forces acting on those objects are the forces that they exert on each other, their total momentum before the collision is the same as their total momentum after, okay? Now remember, momentum is the product of their mass and velocity. So am I saying that after two objects crash that their speed is going to be the same? Nope, I'm not saying that. I'm saying that the product of their mass and velocity is going to be the same before and after. So we have two objects. Before they crash, maybe one was moving faster than the other. So after they crash, in order for momentum to remain constant for the entire system, then that means one slowed down and the other sped up after the collision, okay? So the one that was moving faster is now moving slower, and the one that was moving slower is now moving faster. But overall, if we total up the momentum of the cars before and after, their total momentum together is going to be the same before and after. That's what we're saying, okay? Now, when we talk about collisions, we have two types. Objects either collide and bounce. When they collide, they either bounce off of each other, and we call that an elastic collision, or they stick together and they move off with the same speed. We call that an inelastic collision, okay? So if you and your friend run into each other at top speed, more than likely, you're gonna crash and then each of you will fall back in the opposite direction that you were coming from, okay? That would be an elastic collision. An inelastic collision, well, that's like, let's say you have a big dump truck and it crashes into a car that's not moving. Well, that car that wasn't moving, it's going to be pushed along by the dump truck, and so it's like they're stuck together. So they're moving now as one system. So that's called an inelastic collision. All right. So.
An example again, Bria, sorry.
All right, so we can look at some more examples on this next slide. So with an elastic collision, so I'm gonna tell you this, but we talked about kinetic energy before. So that's the energy an object has because it's moving. So with an elastic collision, the total kinetic energy is the same before and after the collision, same as the momentum. One or both objects, I should say, change direction in an elastic collision. I have quite a bit of typos in this. I need to fix that. An example of an elastic collision happens between, well, we don't call them this, we just call them the pool balls, okay? But they're called snooker balls. So what you play pool with, when you hit one, it hits the other and they go in the hole. That's an example of an elastic collision. We also have elastic collisions happening between gas particles. So elastic collision, one thing bounces off of the other and they change direction, okay? So you can look at the little visual down here. Elastic collision, so The arrows show the direction. So we call this type of collision that's being shown in this picture a head-on collision, when the two objects are both coming from opposite directions. Okay, and they're coming towards each other. So we have a head-on collision. The two objects were originally going towards each other. They crash, and then now they're both moving in the opposite direction. Okay? Then we have inelastic collisions. In an inelastic collision, both objects, and this is very important, share a common velocity after the collision. And kinetic energy is not conserved. So with an inelastic collision, like the dump truck dragging along the smaller car, some of the kinetic energy is converted into sound, heat, and deformation. So, you know, when a car crashes, it crumples up. That's deformation of the objects. A high-speed car collision is an example of an inelastic collision, okay? Cars don't usually, well, in some cases, but especially if there's a big, big difference in size, typically you're going to have an inelastic collision between a big car and a small car, okay? So elastic collision, kinetic energy is the same. Inelastic collision, kinetic energy is not the same before and after, and they share a common velocity. You were saying something? That sounded like Cassandra.
Now I just realized velocity is speed, right?
Oh gosh. Yes. You know this? All right. Now, don't get scared. Take a deep breath. All right. So mathematically, this formula states the law of conservation of momentum. All right. Let's break it down nicely. All this says is momentum before is equal to momentum after. That means that the sum of all the values on this side is equal to the sum of all the values on this side, okay? Now notice what these values are. What is mass times velocity?
Momentum.
Momentum. So I can simply say momentum of object A plus momentum of object B. And I'm going to put a 1 to say before. Okay? So this is the sum of their initial momentum plus the sum of their final momentum. That's all we're saying, okay? But in order to solve problems where we're interested in maybe knowing what the mass of one of the objects was, or what the initial velocity or the final velocity of the object is, then we express momentum, we expand it. Instead of using just momentum, we use the product mass times velocity for each. So that's why there's so many variables. But just remember, mass and velocity, all that means is simply the momentum of that one object, okay? Now, when we talk about elastic collisions, we use this formula just as it is, okay? So for elastic collisions, this would be our formula. Now, in elastic collisions, we are going to use the same formula, but we're going to modify it a bit, okay? What was one of the characteristics of an inelastic collision? That has to do with its speed. What did I say? Go ahead.
To be the same?
Right. The speed after collision is going to be the same for both objects, okay? So if that's the case, then that means velocity A and velocity B are equal for an inelastic collision. Okay? Inelastic. So what I'm going to do, since these two are the same, let's call that V2, V2. There's no need to differentiate between A and B anymore. When we have a sum of two products and one of the variables is the same, we can factor that out. So we can say V2, open bracket, that leaves mass of A plus mass of B. Do you see that?
Yeah.
Okay, and then I just put everything else back on the other side. So mass A, velocity A, mass B, velocity B. Okay, now I'm going to put numbers. So we're going to have two sets of subscripts. We're going to have one, by subscripts I mean the small numbers and letters that we put at the bottom. Okay, these are subscripts. We're going to have two subscripts for each variable. By variable, I mean the letters. So M for mass and V for velocity, they are variables. We're going to have one subscript to tell us whether it's object A or B. Okay, and then we're going to have another subscript to tell us whether we're talking about the initial or the final velocity. Okay, so the mass doesn't change, so we only need to say whether it's A or B. But for the velocities, we need two sets of subscripts. So on this side, the before side, we're going to have velocity A1. Okay, so that's the initial velocity of object A. Follow me? Yes? Good. Then I'm going to put next to velocity B on the before side, I'm going to put a 1 there. That means initial velocity or before velocity of object B. All right? And then the 2 on this side means final velocity. And for an inelastic collision, we don't have to put A or B because it's the same. But if we want to, we can put V2 AB, which means the final velocity of A and B. Okay? And so for our elastic collision, our formula, we can put our subscripts in for this one. So velocity A1, velocity B1, velocity A2, velocity B2. All right, so at the top here, This is what we're going to use for our elastic collision. And this one at the bottom is what we use for our inelastic collision. All right. I'm going to give you a minute. I want you to write those two formulas down, because when I pull the problems up, it's going to be difficult for me to keep this up on here. So just write them down at the top of your paper. So the first formula, this one here, is for elastic collisions. And the second one is for inelastic collisions. Write those down. And then we're going to talk about how we know whether or not a collision is elastic or inelastic. Okay. All right, let's try a problem. Okay. So I'm going to walk you through this one. Then we're going to do one or two more. All right, so on that same paper, I'll get that in a minute. Okay, so let's look at the question. Question says,